Lab 3, Magnetic Field of a Bar Magnet. In this lab, we analyzed how the magnetic field due to a small bar magnet depended on the distance of the observation location. We used the Biot-Savart law for calculating the magnetic field of a dipole. We also had to compensate for magnetic north by ensuring that we were measuring orthogonal to Earth's magnetic field. We did this by making the x component of our magnetometer as close to 0 as we could get it. In the ln of bx versus ln of r graph, the equation was found to be y equals negative 14.079 minus 2.6896x. The n value in this equation is negative 2.6896, which is close to our theoretical value of negative 3. The magnetic moment was found to be 3.8418 ampere square meters, and the perpendicular distance as labeled in the photo to the right was approximately 0.19 meters. The first step we completed in this lab was to compensate for Earth's magnetic north by rotating the phone until the x component on the magnetometer app was as close as possible to 0. We then oriented the bar magnet along the east-west direction, and B net, according to our geographical location, was found to be 48 microteslas. We had to find the location of the sensor within our smartphone to ensure the distance was being measured to the correct point, and mine is indicated in the photo to the right with the yellow arrow. Using the magnetometer app on our phone, we made several different measurements of distance when the x component of the magnetic field was at 20, 70, 120, 170, and 220 microteslas. We then found the magnetic field at a 45-degree axis from the horizontal by moving it up distance d perp in the y direction as well. During this process, we had to correct the y component of the magnetic field by adding it to the magnetic field of the Earth in the y direction. In this lab, we used several different fundamental physics equations, including the Biot-Savart law for an on-axis dipole, which is equal to mu naught over 4 pi times 2 mu over r cubed. We also used the distance dependence equation, kr to the nth, to determine how the magnetic field changed as the observation location got closer or farther away. The equation found from graphing ln of bx versus ln of r was ln of bx equals ln of k plus n ln of r. This ended up being y equals negative 14.079 minus 2.6896x. The table in the top left shows all the different distance measurements while the bx component was at values of 20, 70, 120, 170, and 220 microteslas. The graph on the right shows the line found using all the different magnetic field x components and the corresponding distance components. The bottom table shows the process of finding the magnetic field on a 45-degree off-axis using the perpendicular distance, and it also shows the correction process of the y value. An important calculation was done to find the magnetic moment. We started with the distance dependence equation and set it equal to the magnetic field equation. We then solved for mu, and we knew from the graph equation that ln of k was equal to negative 14.079, so therefore k was equal to 7.68 e to the negative 7. This allowed us to solve for mu, which came out to be 3.8418 ampere square meters. The code section on the left shows the establishment of several constants, measured and calculated values. It also includes the function used to calculate the magnetic field. On the right, I was setting up the 2 on-axis observation locations and 4 perpendicular observation locations. The code section on the left shows where I create the 6 arrows previously mentioned and call upon the magnetic field function for each one. The code on the right is the process of finding the off-axis magnetic field and displaying the arrow that represents it. In this photo, the 2 red arrows represent the on-axis magnetic fields. The 4 blue arrows represent the perpendicular magnetic fields, and the singular green arrow represents the 45-degree off-axis field. The values in the bottom left show the magnetic fields for the perpendicular on-axis and off-axis observation locations, as well as the magnitude of the distance that the off-axis observation location was at. If we hadn't oriented the magnetometer to compensate for magnetic north, our x component would no longer start at 0 and we would be including the Earth's magnetic field in our measurement. If we stuck 2 magnets end to end, the x component of the magnetic field and magnetic moment would be twice as large as well. In this lab, we were able to explore the distance dependence of a bar magnet's magnetic field based on how far away the observation location was. We analyzed these changes using the Biot-Savart law, the distance dependence equation, and the equation derived from the ln Bx versus ln R graph. We also observed that when the magnetometer is moved farther from the magnet, it measures a near zero magnetic field in the x direction. And finally, as the magnetometer moved closer to the magnets, the measured x component of the magnetic field greatly increased.